right, environmental robustness. First of all, I would say that unmanned airships are really going to be a big game changer in the field of infrastructure inspections. Without going into every detail, because my focus is on something else, we have a huge potential for automating manual work with airships. We have a huge potential for being more environmentally friendly with airships, and we have the advantage of flying longer and not crashing like a stone, but having something like a flying airbag, how I like to call it. But on the other side, as you know, airships aren't magic, and also they can't defy physics. So I think when we inspect infrastructure, we have two main opponents, like I would call them. So there is wind, gusts, thermals. Maybe you could generalize it to moving air or movement changes of air. And then there is temperature changes, superheat inside the hull, and atmospheric pressure changes. So you could sum it up as pressure changes of the air. And let's have a look at these two issues. And let's start with the pressure changes. In airship history, there has already been done a huge deal about dealing with pressure changes. And the most beautiful, most advanced way of dealing with pressure changes is, of course, the rigid airship, because it just doesn't care. But then there are these blimps that we love to use as airship drones, because they have some advantages for transporting. And for blimps, as you know, there is these ballonets, maybe one, maybe two, to have an even keel. But there has lately been also new ideas for ballonets or for pressure regulating systems. For example, there is this shape-changing invention by Kielu that has internal tensioners inside the gas bag that kind of squeeze the gas bag together when the pressure isn't sufficient. And also in our team at Rubolun, our team member Mark Summers has come up with a very nice idea for a rubber belt tensioner. So you have this rubber belt around the gas bag, and when the pressure decreases, then this will get smaller in diameter, and you have a covering sheet over it, so you don't have that drag involved. If you want to know more about that, you can ask me later. This has been built and tested by Mark, and I can also show you videos. But today, I want to show you yet another experiment for using a passive ballonet, or a passive pressure regulator, as I would call it. Because these passive approaches, they have the advantage that you don't need these active pumps, these active valves, and the extra material for the ballonet itself, but it kind of works by itself, and it's very easy, not so complex. And one thing we tried together with the team Windreiter is introducing an elastic gore in an otherwise stiff outer hull of a blimp. So our blimp, as you can see here, is actually composed of two layers. We have an inside gas bag and an outside ripstop nylon. And usually this outside hull would not be elastic, so it can't act as a pressure regulation system. But now, oops, sorry. Oh, I got confused here. But now we have this elastic gore over here, and that is able to expand and contract and allow the inner gas bag, that is significantly bigger than the outer hull, to expand and contract. So we did some experiments last Saturday when it was, you won't believe it, 30 degrees Celsius in Germany. So we had our workshop here inside where it was 23 degrees Celsius, and outside in the sun it was 30 degrees Celsius. So we filled the airship inside the workshop and then took it outside, measuring the pressure and the temperature all the time, and also the circumference of this airship hull here. And looking at the pressure, we can see the following. We have here the differential pressure measurement over time. And I'm sorry for the sign, actually that should be positive. I just plugged it into the wrong tube. So please imagine that going down means pressure increases. So what you see here is we filled to 0.5 millibar inside the workshop at 20 degrees Celsius. And that gave us a hull tension that was ready to operate, basically. And then we went outside. Here we didn't measure, but then arriving outside, we had 30 degrees Celsius in the sun, and you see the pressure now increases. Then we have these little spikes here, and every little spike makes a little pop, 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 because that is when these creases of the inner envelope that overlap first, they open up and give room to the expanding helium. And then the sun went behind a tree, giving the hull a little bit of shadow at the tail, maybe 1 meter or so. And that's what you see here. The pressure decreases again. So we moved the hull back into the sun, and then the pressure increased again. So as you can see, these pressure changes are well observable. And now, what does that mean for the ballonet function or the pressure regulation function of this system? As you can see here, we had 12 centimeters of difference in diameter of the hull. That was the expansion. And that means a volume increase of 3.5% based on a calculation with Airship Lab. I love this tool, can recommend it to everyone. So you can see that the pressure regulating function of this core already works in principle. Now if it already does a good job, or if we have to improve something, further tests will have to show that, but I just wanted to introduce this new idea to you. And next, let's have a look at the second challenge, and that is the robustness of an airship in wind. And for our application, robustness in the wind means we really have to reach a very specific position in the air so that we can inspect a certain point of a certain infrastructure. It is very important to have that position and not be 5 meters here or there. And for that purpose, we invented this unique propulsion system that gives our airship the maneuverability of a helicopter. Many of you already know me and have seen that in action already. Some may not, so here is the video again, just showing how this airship is maneuverable in all directions. Here I'm simulating some wind gusts by pushing against it, and you can see that the autopilot moves the airship back into its original position immediately. And you can see the vertical up and down movement that is possible. And yawing around its own axis. Backwards flight. Forwards, of course. And the special movement, the lateral movement, or the so-called crabbing. So it's really maneuverable in all directions. And this, as I said, is important when we want to inspect infrastructure, because there we don't want to fly into a power pole, right? So let us see how this maneuverability plays out when it counts. And our hearts were beating quite wildly, but it did work out. I'm just going to show you this video that is from a pilot project with a utility operator here in Germany, NetzeBW. And for NetzeBW, we did a detailed inspection of power poles. And detailed means just like they do with their multicopter drones. Positioning the airship at a specific point, then making 5 images so that bolts, nuts, isolators, everything can be seen from the foundation to the very tip of the power pole. And here you can see some detailed pictures that were taken during this flight. Who is living there? And then if the first position, every picture is taken, then the second position will be reached shortly. Here you can also see how far we can actually zoom in so that the utility operator, power grid operator can actually see, is the nut still there, or is there a broken or a used insulator that might cause a short circuit or something. Yeah, and here we are reaching the second point, or the second viewing angle, again making pictures, and this is done at a distance of around 15 to 25 meters. That was the safety distance we are keeping. When we transition to the next pole, we keep an even bigger distance because that's just safer and it has no disadvantages. And then again, we position, make the pictures, and fly on. And all that, by the way, was done in gusts of up to 20 kilometers an hour. And the airship was still able to maintain the position and fly in a stable manner. Here you see the flight path around the 3 poles that we inspected. We'll come back to that in a second. So this was the flight path. The R marks the power poles, and we inspected 3 power poles in a row, first on the one side and then on the other side, and then returning to our takeoff position. And here you once again see how a detail of this inspection looked like. And now the big question is, so how precise is positioning actually? And this can be seen here. So again, this is the flight path, and in red you see the programmed path, and in green you see the actual flight path. So that is where the airship moved along. And when we zoom in to this position where the airship was standing at a certain point, then we can see that this was the desired position and this here was the actual position, and the accuracy is on average around 60 centimeters, and the precision is in a bounding box of 60 times 30 centimeters. So that is how precise the airship was able to keep its station in these gusty wind conditions. And again, if we zoom into this here, we can see that while we are on the way to somewhere, we have an accuracy of around 3 meters in our flight path following. So this is how we manage a flight path accuracy with the help of our propulsion system. And then there are, I just want to join, where is he? Spencer. I want to join Spencer. Sometimes only a nosedive helps. For example, if there is a bad thermal that is pushing your airship up, you just need to push the nose down. But you don't necessarily need to crash. Thank you.